Okay, so we are going to look at Tresca criteria now. Okay, so we're going to look at Tresca U criteria. So where we finish off on Tuesday, we construct the operating bracket for Tresca's U criteria. Okay, so we if I were to draw this, so this is the operating uh, criteria or operating region within Tresca criteria. So you can see over here, I'm going to have two axes. So one is known as stress A, and the other one is stress B. And then let me define stress A and stress B are the principal stresses. Okay. And then we know that Tresca define a U criteria, yes or no, a U magnitude based on the material behavior. So that will be our stress U, right? And based on Tresca, the yield in tensile and the yield in compression are the same. Okay, so from Tresca, the yield magnitude for tensile and compression loading is the same. Okay, so over here, that is our stress U, and then over here, that is our minus stress U. Okay, so on Tresca's criteria, the operating, so we call this the first quadrant, second, third, and fourth. Okay, so for Tresca, this is the operating bracket that he has constructed, and I'm going to explain why this operating bracket. Okay, so he states that if both the stresses are positive, as in the first quadrant, they have to be inside the square bracket. So this is the operating. Okay, in the shaded region, the material will not fail. Then if in both are in compression, stress A and stress B are in compression, the material shall not fail. Okay, so in this region. And then if one stress is tensile and the other one is compressive, right? Then he construct a slope. Okay, and this is in the second quadrant, and this region, the structure will not fail. And likewise over here, right? So within this boundary, the structure will not fail. Okay. So I'm going to plot on Mohs circle, right? So this is stress A and stress B. But how does this look like in Mohs circle frame or in Mohs circle domain, right? So I'm going to call these points. Okay, I'm going to call this point. So this is my point one. Somewhere over here is my point two. And somewhere over there is my point three. Okay. So what we can say in point one is stress A is at U, stress B is at 0, right? Point number two, stress A and stress B have magnitude half, in fact. In stress three, stress A and stress B are at its U. Okay. So let's now construct on Mohs circle. So we're going to look at Mohs circle now. Okay. We're going to look at Mohs circle. So now going back to Mohs circle. So over here, This is my normal stress. I repeat again, this is Mohs circle, yeah? And this is our shearing stress. Okay, so this is our shear. Element rotate clockwise and element rotate anti-clockwise. Okay, and then we have our maximum shear line. So this is our maximum shear line. So the circle cannot go beyond that. Right? And then this is the other maximum shear line. So in fact, I should have drawn it bigger. My apologies. Okay, so this is our Mohs circles. So like before, anything that's outside this bracket, the material will fail. Okay. So if we look at point 1 that I've done on the criteria, right? Point 1, P1. P1 states that when stress A is equal to the yield, okay? So this is my one of my point. So this is my stress A, right? So this over here is my stress A at 1, P1, okay? And then at another point, you have stress B at point 1. So stress B, what we can see at stress B is over here, right? Because it has zero stress. Okay, so stress B at point 1. Okay, so from here, there are our principal stresses. Now we can construct a Mohs circle. So we realize that it's all within, is the maximum diameter of the circle or maximum radius that we can draw. Okay, so that's our first circle. So now if we look at point 2, so point 2, I'm going to use a different color now. Point 2, I'm going to use green in color, right? So stress A at point 2 still remain at the same point, right? Stress A at point 2 still remain at the same point. But if you look at point B now, right? Our stress B at point 2 is half. So over here, now this is where it is. So this is stress B at point 2 now. Okay. So remember, stress A and stress B are its principal stress. So now we can construct another circle. Okay. So what you can see, the circle, no doubt, is interesting, yeah? The stresses are increased, right? The diameter of the circle become what? Smaller, okay? But it is still within the bracket, okay? So this is for tensile. If we go into compression, if we work onto the third quadrant, it's going to look the same, okay? So now you know the response between the first, right? You know the response of the operating bracket between the first and third quadrant, right? The first and the third. So the third quadrant is just everything in what? Everything in compression. So the diameter of the circle just keep on reducing. So if you look at point 3, which is nothing to draw, the circle is a dot, which is ridiculous, right? If we get, so at point 3, this is stress A at point 3, and also is also equal to stress B at point 3, right? Because both are at its yield, right? At point 3. So it's no more a circle, but rather a dot. As long as within the yield, you are fine. Okay. Now, let's look at the second and the fourth quadrant now. Okay. So let's look at the second and the fourth quadrant. So I'm going to sketch the same thing. Okay. I'm going to sketch the same thing. So this one is for first and third quadrant. And then the next one is for the second and the fourth. So again, this is shear stress, element rotate clockwise, anti-clockwise, normal stress, and then we're going to sketch the operating boundary. So 2, 4, 6. So this is our operating boundary. Okay, so anything out here, the material just fail. Or will yield, not fail, okay, will yield. It's not a failure criteria, but it's a yield criteria. So you go from elastic to plastic. Right. So I'm going to now call this our point over here. This is our point 4. Okay. Then we are going to look at point 5. And then we'll look at point 6. Okay. P6. All right. So at point 4, stress A is at the maximum negative, right? So our maximum negative is over here. So this will be our point 4, right? Or stress A at point 4. And then the stress B now is at 0. Okay, so this is our stress A, our stress B at point 4, right? So again, this is straightforward. We can construct one circle. Okay, and then the next one at point 5, again, I'm going to use a different color for point 5, right? So at point 5 now, stress A is at compression, right? Halfway of the yield. So this is my stress A at point 5. And this will be my stress B at 0.5. Okay. So what you realize now is the diameter of the circle remains the same, but it's shifting within the operating bracket. They're shifting within the operating bracket. Okay. And lastly, at 0.6, where stress B is at its maximum, so I'm going to use a different color now. So over here, this is stress B at 0.6. Okay, and then this is stress A at 0.6. Okay, so what happened now is the circle is within this operating boundary now. Okay, so this circle is for 0.6. The next one, the green one, is for 0.5, and the black one over here is from 0.4. So what I'm trying to tell you is this. So Tresca, what he did is he constructed this diagram first. Okay, he drew all this, right? He looked at the possibility for his criteria to work. Then he came up with the graph above there. Okay, so that's how the relationship of Tresca operating bracket is seen in this diagram, like this. Okay, so because he have drawn all the situation, so the situation in first and third quadrant is the diameter of the circle gets smaller, but it's still within the operating bracket, whereas in the second and the fourth quadrant, sorry, so this is the second and fourth quadrant, what's happening is the diameter of the circle is fixed. It's just shifting in the operating bracket, moving left to right, and as long as within the operating bracket. And we know that over here, right, these are all our yield, right? This line over here is all our yield, and this is also our negative yield. or yield in compression, and the top is